The second speaker is Christopher Trapp from the ETH Zurich. He will talk about tensor network decoding of arbitrary 2D Pauli codes. Please go ahead, Chris. Hi, yes, I can hear you.
Okay, cool. So, okay, this is visible, I'm going to assume. Right, so thank you to the organizers for this opportunity. So as was said, I'm going to be talking about tensor network decoding of arbitrary 2D Pauli codes today. So one of the nice things about Pauli codes, especially under Pauli noise, is that the optimal decoding procedure can be succinctly described. And it's given by something called the maximum likelihood condition. This is referred to as the maximum likelihood decoder. So here, all you have to do is you take the syndrome data, you calculate the associated error classes, and then you just have to maximize the, you have to find the error class with the highest probability in your error model. So this gives you a really succinct description of optimal decoding for these codes, but obviously there has to be a catch, otherwise, you know, it can't be that easy. And the catch is that these error class probabilities are exponentially large sums, right? So for a stabilizer code, for example, this involves a sum over the entire stabilizer group, right? So this is the thing that makes this this expression not so easy to do in practice. The technique that we look at in this paper to sort of practically attack this is to say, well, you know, these class probabilities involve exponentially large sums that are potentially difficult to evaluate. That's also true of tensor networks. Can we connect the two and then, you know, leverage tensor network techniques and sort of pull them back to give you a decoding scheme? So there's, you know, been work for quite a while, sort of looking at the connection between quantum error correction and tensor networks. There's even some previous, there's some previous work looking at this explicitly to do tensor network decoding. But these constructions were very code specific, right? So this work, for example, looked at the toric code specifically. So in some previous work with my PhD supervisor, Steve Flamea, we actually looked at, this is sort of a side effect, we're actually looking at the connection between these class probabilities and statistical mechanical models. But a side effect is that it also lets you give a general construction to take you from these class probabilities to tensor networks, which is pretty handy. So that's the work that we sort of built upon. And this works for an arbitrary Pauli code. This lets us reduce the problem of optimally decoding a 2D code to the problem of contracting a 2D tensor network. So how do we go about that? So all the previous work was built on this algorithm by Verstraete and Serac, which I'm just going to briefly outline. So here the idea is you start with some tensor network that's in, say, a 2D grid. You start by considering the leftmost column. You then will absorb in the next column by doing a tensor contraction. This now causes these bonds to grow. And if we didn't do anything, this would cause an exponential growth in these bonds eventually and give an exponential time algorithm. But here we can use a tensor network technique known as bond truncation, which lets us essentially compress this back down. You can think of it like a lossy compression. So this is a heuristic. And then, you know, you rinse and repeat, right? You keep doing this until eventually you're just left with a single column. And then these are just matrices you can multiply together until you have an answer, okay? So as I said, all the previous work is built on this algorithm. So what's the problem? So the key problem is that this method is built on this idea of columns. And so this limits the applications of it. So the first issue is, you know, what if I have an irregular network? What does a column mean in this case, right? You maybe come up with a definition, but it's not straightforward exactly how you would define columns in this setting. The other more subtle one is, you know, how do we find these columns algorithmically, right? So in previous work, looking at decoding on, you know, things like this rhombile lattice, this is from a previous paper, the way that it was dealt with there was you sort of massaged it into the square grid, but this was, you know, done by hand, right? You had to sort of, you know, sort out this network. It wasn't done, you know, algorithmically, right? I propose in this paper a Sweepline contraction algorithm, which sort of extends this Frustrata and Serac algorithm, but alleviates both of these by removing this notion of columns from it. So obviously, with time constraints, I don't have time to go over the full details of the algorithm, but I have a little animation here on sort of the rough idea. So here we sort of are going to sweep along the network as we go, contracting in tensors into this 1D tensor network here on the left. So the key thing is we have no notion of columns here. This is perfectly well defined for random networks, and it's completely algorithmic. I didn't need to massage the network at all as I was beforehand, right? You just put in a random network and it'll run. This is the idea, at least. Okay, so this is a nice proposal. Does it work? So to check that it worked, I looked at a bunch of codes that we ran into this to test it. Most of the codes that we looked at were based on the surface code, which is a generalization of the toric code. The nice thing about the surface codes is they're very flexible. You can put them on any planar graph. These are codes defined by having these sort of planar, plaquette and vertex type generators, much like the surface code. So we looked at a whole series of surface codes on regular graphs, such as triangular, hexagonal. We also looked at a bunch on irregular graphs, so random triangulation, random tetravalent, random trivalent, things like this, which is something that a lot of previous decoders can't really deal with. For completeness, we also looked at a few non-surface codes in 2D. So we looked at the color code and something called the subsystem surface code, which is a non-abelian version of the surface code. So here's a sort of summary of our results. Again, obviously I don't have time to fully go into details, but the long and the short of it is in all of these situations, we got very, very close to optimal, which is quite nice. So, here are the classes of codes that we ran it on. We ran it for bit flip, phase flip, and depolarizing noise, just as sort of tests. And in all of these situations that had previously been run, to my knowledge, this gives sort of state of the art, some of the best thresholds known. And we're able to run for a bunch of codes that previous decoders could not run on and give seemingly optimal thresholds, which is quite nice. Okay, so I think this leads in my conclusion here. So we showed a technique that gives you, highly flexible and effective 2D decoding in general, which is quite nice. There's a bunch of obvious future directions, measurement errors, 3D, things like that. These are my links if you want to contact me. And yeah, thanks.
Thanks, Chris. There's one question from Jonas Helsen. Does the performance of the algorithm, both in the threshold and in decoding time, depend strongly on the choice of the sweep direction?
So yeah, that's an interesting question. We didn't really look at the sweep direction very much. So I mean, for these regular graphs, it shouldn't. Well, it's an interesting question. We didn't look at that very much. That's an interesting question. It could, and there's another question of there's some flexibility in the embedding. So as well as sweeping in a different direction, you could maybe try and adjust the graph to speed it up. Yeah, you could probably speed things up in that way. The thing that we really wanted to highlight was the flexibility, the fact that you can just throw a random graph into it and it will run. I'm certainly not suggesting it's very fast, but it's very flexible in that regard. So yeah.
Okay. Thank you, Chris. So I think it's